Hello, in this video we are going to talk about Taylor's theorem with Lagrange form of the remainder. This is actually the main theorem in this topic, and that is the reason we were interested in talking about Taylor polynomials in the first place. So this is a theorem that helps us to approximate the value of a function with its Taylor polynomial, and it gives us control over the error that we are making in this approximation. The proof, of course, of this theorem is rather technical. It needs what is called the generalized mean value theorem. If you're interested, you can, of course, look it up in the course book, and if you're interested to discuss, if you have any difficulties, we can discuss it during the breaks or after the lessons. Okay, now my point here is to actually introduce what the content of this theorem is. So Taylor's theorem with Lagrange form of the remainder. So here let n be a non-negative integer, 0, 1, 2, 3, etc. and f be a function such that if n plus first order derivative of that function f exists for all t on an interval containing a and x. Let p sub n and a of x be the nth order Taylor polynomial for f centered at a. Then this theorem guarantees the existence of a c between a and x such that the value of the function at x equals to the value of the Taylor polynomial, the nth order Taylor polynomial about a at x plus this term. The first n plus first derivative of the function calculated at c. This is the c which is guaranteed. Its existence is guaranteed by the theorem, divided by n plus 1 factorial times x minus a to the power n plus 1. And I hope that you see that this equality is 100% accurate. Somehow, intuitively, it means that if I drop that one, then this should change to approximation symbol. Okay, so that's the idea. Okay, let me point just from the beginning that this theorem is not capable to give you the exact value of c. It rather actually guarantees the existence of c somewhere between a and this x. Okay, it guarantees that there is a c with this property that makes this equality 100% accurate. But as you will see, this is good enough because it will allow us to give an estimate about the error of the approximation we are making. And this term that you can see here is called the Lagrange form of the remainder. It's simply the remainder. And in your book, this term is denoted by E sub n and a x, and of course, as usual, if a is known from the context, we just suppress it from here and suppress it from there as well. So in other words, if I want to write it, we can write that f of x is equal to p n and a x plus that remainder is denoted by e for error. In some books, of course, they denote it by capital R for remainder, but I'm following your course book. So this is the Taylor's formula. This formula is called Taylor's formula, and that is the Taylor's theorem. So if I want to suppress a's, this can simply be written as Pnx, and then I have En of x. So this is Taylor's formula. Okay, I think that's a good idea to actually expand the formula, so let me plug in the Taylor polynomial formula here. So it becomes f of a plus f prime of a divided by 1 factorial x minus a, and then plus f double prime a divided by 2 factorial x minus a to power 2, and we continue until the nth order. So it becomes the nth order derivative of f at a divided by n factorial x minus a to power n. pretend that you want to continue one more step. What would happen? You would have written f n plus first order calculated at a divided by n plus 1 factorial, and then x minus a to power n plus 1. So if you want to write the n plus first order Taylor polynomial, that is what you have written. But now the only thing is that when you want to write a Taylor formula, this a here should be switched with some c, which you know is between a and x, nothing more. In this way, it is not hard to remember the form of the Lagrange remainder. So yeah, anyway, that is my advice for you how to memorize the Lagrange remainder formula. Okay, and one more thing that I want to mention, if you want to get a feeling what this theorem is, this is a generalization in principle of the mean value theorem. So in principle, if you know n is mentioned to be a non-negative integer, let us take one special case that n is indeed 0 and write the formula, Taylor's formula. So the Taylor's formula will tell me that f of x is equal to p0 of x plus e0 of x. Okay, but what is p0 of x? p0 of x is nothing except the value of the function at a. So it means that I take only the 0th order part. So this is nothing except p of 0. But let me write e0. So this is the formula for e sub n, but here I have n equals to 0. So this becomes 1. So this is the first order derivative. So e0 of x becomes equal to the first derivative of f calculated at c divided by 1 factorial, because n is 0, and x minus a to power 1. Yes, so this is essentially f prime of c times x minus a. And what is c? C is between a and x. So that is the special case of Taylor's theorem for the case that n equals to 0. But now if I plug this and this back into the Taylor's formula, what do I get? I get f of x equals to f of a plus f prime of c times x minus a. And of course, if you now move f of a to the left and divide everything by x minus a, so what happens? This becomes f of x minus f of a divided by x minus a equals to f prime of c. And I hope that you remember this is nothing except the mean value theorem. Yes, because when you say that n is 0, it means that it is guaranteed that my function is differentiable, so it is automatically continuous, so I can use mean value theorem on the interval between a and x, and that is exactly the mean value theorem. So I just want you to know that this is the generalized version of mean value theorem. Okay, now let us solve one example to see how Taylor's formula works in practice. This is example 10 in lecture notes. Use the second order Taylor polynomial for f of x equals to square root of x about x equals to 25 to approximate square root of 26. Estimate the size of the error, so that's the power of Taylor's formula, and specify an interval that you can be sure contains a square root of 25. Okay, before starting solving the problem, I just want to mention one point here. So here, x equals to 25, the point around which we're supposed to do the Taylor expansion, is proposed in the problem. If it weren't, it was not hard for us to guess x should be 25. Why? Because 25 is the closest number to 26 for which we can calculate its square root easily and precisely. So it doesn't mean that Taylor's formula will not work if I have chosen a different number. For example, I could have chosen x to be 20 and write my Taylor polynomial around 20, because 20 is also safe. As far as you can differentiate your function appropriate number of times around the point that you choose, Taylor's formula will definitely work. But the problem is that it is not optimal in the sense that if I want to reach some level of accuracy for my calculations, if I don't choose it appropriately, if I don't choose the initial point appropriately, I will make life hard for myself. So I have to go further and further into the Taylor polynomial. I have to keep more terms in Taylor polynomials in order to reach to the same level of accuracy compared to the case that if I have chosen the initial point more optimal. Okay, so that is important. So I just want you to know that Taylor's formula is completely generic and it will work even if you don't choose it appropriately, but then of course you will make life harder for yourself. Okay, anyway, here the problem is given to us, so I have to go to second order. So n in this problem is 2, and the point A is given to be 25, and my function f of x is equal to square root of square root of x, and I want to estimate square root of 26 approximately. Okay, so I would write Taylor's formula for n equals to 2 and a equals to 25. So I would write f of x is equal to p sub 2x plus the error term, or the remainder term, e sub 2x. But what is p2? So we learned about how to write Taylor polynomial. I want to write my Taylor polynomial for the point a equals to 25. So it becomes f of 25 plus f prime of 25 divided by 1 factorial multiplied by x minus 25, and then plus f double prime of 25 divided by 2 factorial x minus 25 to power 2. And now I have to write e sub 2. E sub 2 is just, you can pretend that you go one step more into Taylor polynomial, but the only difference is that instead of writing 25 in the derivative, you replace it with c. So it becomes f triple prime at c divided by 3 factorial x minus 25 to power 3. But you have to remember, what is c? C is between a, which is 25, and x. Okay, so let us start now calculating these coefficients. So in order to do that, I need to differentiate. So f of x is equal to square root of x. If you don't mind, let me write it as x to power 1/2. It makes it easier to differentiate consecutively. So this means that if I want to calculate f25, it is 25 to power 1/2, which is simply 5. But now if I differentiate it once more, it will be 1/2. Sorry, if I differentiate it, 1/2 will go down, so I will have 1/2 x to power 1 unit less. And then if I want to calculate f prime of 25, I replace x with 25 to the power of minus 1/2, so it is 1 over 2, 5 to power 2 to power minus 1/2, so it becomes 1 over 2 pi to the power of minus 1, which is 1 over 10. And now f double prime of x, so this is my f prime. I want to differentiate it once more, so 1 over 2 goes down, and then 1 will be deducted from the exponent, so it becomes minus 1 over 4 x to power minus 3 over 2. And then f double prime of 25 becomes minus 1 over 4 x to power, 25 to power minus 3 over 2, and exactly as before. So it's minus 1 over 4, 5 to power 2 to the power of minus 3 over 2. So it's minus 1 over 4, 5 to power minus 3, minus 1 over 4, 1 over 125. So it will be minus 1 over 500. And also I need f triple prime, so let me do that. So what happens? This minus 3 over 2 goes down, so it becomes positive 3 over 8, x to power 1 unit less. So then it means that f triple prime calculated at that c is 3 over 8 c to power minus 5 over 2. I prefer to write it with positive exponent, and of course use a square root sign. So I would write it as 3 over 8 c squared, the square root of c. Yes, because if I bring it down, it becomes 1 over c to power 5 over 2, and c to power 5 over 2 can be written as c squared times square root of c. Now, if I plug all these numbers and these expressions back into my formula, then I will have f of x is equal to, let me write it a little bit lower. So f of x is equal to f of 25 is 5 plus f prime of 25 is 1 over 10 divided by 1 factorial. It remains 1 over 10 times x minus 25, and then plus, so this number, which is this, divided by 2 factorial, which is 2. So it will be minus 1 over 1000 if I divide this by 2. So let me clean this. So it becomes minus 1 over 1000 x minus 25 to power 2. And then this expression divided by 3 factorial. So 3 factorial is 3 times 2 times 1, which is 6. So I have to divide this by 6. So 6 will be multiplied here, 48, and these will be simplified. So it becomes plus 1 over 16 c squared square root of c. But what is c? C is between a 25 and x. So this is the formula actually that we have now. This is what we learned today in Taylor's formula, okay? Okay, now what we are supposed to do, we are supposed to calculate a square root of 26. So it means that a square root of 26 is nothing except that f of 26, yes, because my f is the square root of x. So it means that go here and replace x with 26. Okay, and then what happens here, c will be between 25 and 26. Okay, so let me move everything to a new page so that we have enough space to write. Okay, so a square root of 26 is equal to f of 26. And now I replace x with 26 everywhere in this formula. So what happens? It becomes equal to 5 plus, if I put 26 here, it becomes 1. So I just simply write 1 over 10 minus, the other one is 1 to power 2, but I would have minus 1 over 1000. And then plus the error term, 1 over 16 c squared square root of c. But then here c is between 25 and x, but x is 26. So what I can safely write is that c is between 25 and 26. Okay? Oh, sorry, c is between 25 and 26. Okay, but this is easy to calculate. So a square root of 26 is equal to 5 plus 1 over 10. So let me write it as 0.1 minus 0.001 plus 1 over 16 c squared, the square root of 6, which is equal to 5 plus this one minus that one becomes 5.099 plus 1 over 16 c squared square root of c, and c is between 25 and 26. Okay, so the approximate value for a square root of 26, if we choose the second order Taylor polynomial, is this number, and this is the error that we are making. But now, because of I don't know exact value of c, that would be fantastic and ideal, which is not like that. So, but I know c is somewhere between 25 and 26, so I can have an approximate I can have estimate over this error. So when usually they talk about the size of the error, they are interested in the absolute value of the error that you are making. Okay, but here, of course, C is a positive number, so this expression is positive. So what does it mean? It means that this estimate that we have made, this approximation we made for a square root of 26, is less than the real value. Because to reach there to the real value, I have to add a positive number to my approximation. Okay? But let me estimate how bad is this approximation, so I want to have a control over it. Okay, so C, this expression 1 over 16 C squared square root of C is definitely less than if I replace C with 25, yes? So why is that? I want to find an upper bound of my error. I want to see what is the error that in the worst case scenario I am making. Yes. So you know that the minimum value of C is 25 and it doesn't reach to 26. So this number is definitely less than this number. Why? Because the numerators are the same, so this 16 is the same, but C is greater than 25. So if I put a number greater than 25, this fraction becomes smaller than this fraction. That is simple. And then I can calculate this. Hopefully we can do it without calculator. So this is 16, 25 to power 2. I have it in my memory, 625, and then square root of 5. So if you multiply them, so I don't know, so this is 3125. I don't know, you can put it in the calculator, but let me do it in my head. So I multiply, I write it as 4 times 4, but 4 times this one is 1215. This becomes very easy, so it's 50,000. Okay, so this means that if I say this square root of 26 is approximately 5.099, the error that I am making in the worst case scenario is less than 1 over 50,000. So this shows me that yes, this is a really good approximation. Yes. So I can write it in decimals. So if I write it in decimals, it will be 0. How many zeros? 1, 2, 3, 4, yes, and 2. So this is the upper bound of the error that I am making. So if I am interested in the interval that I am sure that square root of 26 lies there, the interval would be this number, yes, up to 5099 plus 0, 0, 0, 0, and 2. So this is the interval that I am certain about, that the square root of 26 belongs to that. Yes? Which can be written, of course, 5.9099, and that number will be 5.009, another 0 and 2. Oh, this is 9. Yes? So this is the interval that I am certain about, that the square root of 26 lies there. So you see that this in practice is a very powerful theorem. It not only gives you the approximate value for the square root of 26, it is also telling you how much error that you are making in the worst case scenario. But be careful, it will not give you the exact value of the error. Okay? Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.